lab observed more than 500 photons at energies greater than 0.1 GeV. That's the most that it ever observed. And then there was a prompt optical detection, magnitude 7, one of the brightest ones again. But in Swift and other detectors, it was, more or less normal behavior. Light curves, they look more or less like that. There is the usual delay of the GeV gamma rays. And so one of the interesting things is that the GeV light curves, they last for a long time, and that's not that unusual, but they seem to be somewhat flatter. The time decay is slower than typical. And so that was one of the things that was somewhat interesting. The second component is not unexpected, that has been seen in algorithms before. So what the Fermi-Laut analysis concluded was that the ratio of the GeV to MEV fluence is equivalent 20%, that's common. The highest energy photons, they suggest that the Lorentz factor is greater than about 450. That's typical of the lab burst, the burst which show GeV emission. But the GeV photons, they come mainly after the MEV photons have faded. So they may come from disjoint regions. So that again suggests that two different shocks are producing the low energy radiation and the high energy radiation. And one interesting constraint is that there was a 95 GeV photon observed, and that cannot be explained by synchrotron radiation, because with synchrotron radiation you can calculate what is the synchrotron loss time, what is the amount of time needed for the electron to lose its energy, and if that time is shorter than the time needed to make one full gyration, then you cannot, then it's not synchrotron radiation. You have hit the quantum limit. So you need some other explanation than simple synchrotron radiation. Some inverse Compton explanations can do it, and also some hadronic explanations. And the flattening of the light curve can be understood if you continue injecting energy into the jet. So Swift and Batt did corresponding analysis. I won't go into detail in these. It concluded that no significant surprises except for the fact that the GeV, 96 GeV photon cannot be explained by simple synchrotron forward shock. That's okay. In reality, it was never expected to be synchrotron forward shock, although some people had produced, simplified models. So when I mentioned to you that with the first launch of Fermi, there were again a number of models. Some of them had argued that everything can be explained with forward shot synchrotron. This is an oversimplification, and this just proves it that that oversimplification is indeed not valid in all cases. Another satellite also concluded that there are no great surprises. So an interesting, more detailed view is what the optical prompt detectors, the Raptor, showed. So what they showed is that you need two separate episodes of the radiation, which you can associate with the reverse shock flash at the prompt component, and then the afterglow reverse shock and the afterglow forward shock. And that in the afterglow you need continued injection of energy. This is how you fit it. So here is the prompt reverse shock flash, and then the continued injection reverse shock, and the continued injection forward shock producing the optical light curve. And then with the same model you can fit the X-ray afterglow and much of the gamma ray afterglow, the GeV afterglow up to 100 GeV. You have to, however, you don't fit the 95 GeV photon. For that you have to do an inverse Compton or a hadronic explanation. So there have been a number of other theoretical papers on these bursts. But as a summary, these bursts didn't really challenge much the standard model. As I was mentioning, most of the components can be understood. The only query is, whether the GeV radiation. So there are these extensions of the standard model, like continued injection, the inverse quantum from a different source of photons, or from the synchrotron self-quantum. So the doubts are in these, which of the variants of the extensions of the standard model do you go? So it's you have a couple of options that can explain the observation, but you're not sure which one of them is. All of them are reasonably plausible. So you're not really worried that you're missing something, but you can't make up exactly your mind of which of those it is. The gross features are reasonably well explained with the standard model of either prompt emission from an internal shock or photospheric emission, and the afterglow from the external shock and the reverse shock from the external shock. Now, there are some general issues that remain, and mainly they remain with the prompt emission, some of them with the high energy emission. So I mentioned to you the band spectrum, and that might come from the internal shock, where you can ascribe it to synchrotron radiation. That's a nice model, the internal shock model, and it's more or less unchanged since 1999, but there are some objections to it. One of them is that the electrons cool very fast, and if they cool very fast, you expect the spectrum to be frequency to the minus a half, and typically the spectrum has a different slope than that. So that's surprising, and it's unclear what is the problem there. The other is that in a synchrotron spectrum, when you accelerate electrons, the slope above the peak frequency, which corresponds to the minimum Lorentz factor of the electrons, can be well understood, but then there is the low energy asymptote, which you expect to be frequency to the 1/3. And sometimes the slope is steeper than the frequency to the 1/3. So that's difficult to understand in a simple synchrotron spectrum. The third problem is that internal shocks, they occur because you have two shells colliding with each other. And so there is a mechanical efficiency. You're converting bulk kinetic energy into random energy of the electrons. And there is the mechanical efficiency is relatively low. And in addition, then you have radiative efficiency in a particular observing band. So internal shocks typically have a low effective radiative efficiency in the LEV band. So you wonder, what solutions there are for that. Maybe the radiation mechanism is a different one. There are different possibilities, jitter radiation, or that the electron distribution is different. Or maybe turbulence plays a role, and you have, more gradual heating, not a sudden shock heating. Or maybe there are magnetic fields and magnetic reconnection. The magnetic reconnection produces a more effective high radiative efficiency. So these are things I'll briefly mention in the next lecture. Yes, Mr. Much. So I'm finishing up. Just briefly, I'll say that it is extremely important, of course, to have accurate and plentiful data. And Swift and Fermi have provided a lot of new information. So a lot of advances have been made since the early Vela times, when all we knew is that gamma rays are being produced somewhere out there by we don't know what. Now we know, where they're coming from, in what galaxy do they occur. We know that they're stellar events, and we know more or less we know very well what the long bursts, what type of stars produce the long bursts, and we are fairly sure what the short bursts are produced by. We have clarified that the emission is collimated in a jet, that it's highly relativistic. The jet structure is being probed now. We're beginning to resolve details of what is the jet structure. And we're getting very good evidence about the role of shocks, the forward shock, reverse shock, etc. From gamma ray emission, so the one that lasts tens of seconds, that's the one where we have a model, the internal shock model, which is the workhorse model. Everybody uses it, especially observers, because it's a simple model, it's easy to calculate, it's easy to model it. But theorists know that the internal shock model has some issues that are nagging, and that, for the past 10 years we have been working at finding a good alternative or a way to modify it. And I'll mention some of these modifications in the next lecture. The other big debate is what's the role of magnetic fields. In astrophysics, of course, magnetic fields are always present because the plasmas are typically ionized as soon as you have high energies. So once you're talking of KEVs, MEVs, GeVs, the plasma is ionized, you have charges moving around, you will have magnetic fields. So the magnetic fields can play a huge role. Sometimes they can be dominant. And if you have magnetic fields and random motions, you have reconnection, and then you liberate a lot of energy, you can accelerate particles. So that is a very attractive idea, and it's being, played with, but it's very difficult to calculate. And so their role is the focus of increased attention, and it's still, being worked on. So I'll mention some of these in the next lecture. So that's it for now. I will stop here.
Thank you.
I have a question. You mentioned that when we talk about the jet structure, you mentioned that the peak energy is proportional to the power of the isotropic energy. Can we understand the power?
How do we know that?
Yeah, how do you?
Oh, it's just phenomenological. So you measure the spectrum, so you have the break energy, and you measure the flux, so you have the isotropic equivalent.
Can we understand why the power is
Oh, why that relation?
Yes.
Okay, so I didn't have time to go into that, but it's you can actually find a relationship like that in a type of models that I'll talk about in the next lecture. So they're one of the alternatives to the internal shock model production of the gamma ray prompt emission is that the gamma ray emission occurs in the photosphere. And in that case, you actually get a relationship just like that. So you can actually explain it in that type of model. In the internal shock model, that relationship doesn't come out. So that's another of the flaws of the internal shock model. But it's that phenomenological relation is roughly understood with the photospheric model.
Okay. Questions? Student?
So I'm sorry, I've been going very fast and covering the material in a somewhat superficial manner to get the whole material in relatively short time.
More questions? Okay. Okay, then we are going to the long break. So this is the second 2 hours. Having the 30 minutes. So come back on